All right, welcome to another exciting episode of Advanced Level Chemistry here at Spain Park High School. Today is Monday, December the 9th. Jonathan, what are they supposed to do if they're liking these videos?
Hit that like and smash that subscribe button.
All right, and feel free to ring that bell for notifications.
My fault.
All right, so we are Monday. We get today, what we have to do is we're going to review and refresh Lewis dot structures. So all of the sheets that I want you to have out is I want you to have out this Lewis dot structure sheet that we were just working on. I want you to have, it's always a good reference to have the how to draw the Lewis dot structures directions, but I also want you to have this handy to where you can look at this, okay? Because you're gonna have this on a test, but you're gonna need to be able to apply all the things all the Lewis dot structures that you're doing. So we were looking at these Lewis dot structures. You did many of them Friday in class. I'm assuming you got at least through 5 when you were building them. Now what I want you to have on this sheet, and I am going to give you credit, a classwork credit grade on this, so make sure that number 1, you have the Lewis dot structure for all of these on this sheet. Okay, Lewis dot structure for all of them, and I'm going to go through and do a lot of them, the rest of them today with you. We're going to do them as a class, but you also need the shape for each one. Okay, because the shape is going to be super important. And then today, after we kind of review this, then we're going to start talking about how does the shape affect the properties, and then we're going to talk about molecules either being polar or non-polar. Are they going to have a positive and negative end, or are they going to be just kind of evenly distributed with the charge? And that's going to be huge as far as what their properties are going to be. So then we're going to tie it all up. Now, unfortunately, we don't have time then to kind of tie it all up on how then the shape and the characteristics of the molecule affect their properties. We're going to do that first thing as soon as we come back from Christmas. We'll then talk about then the properties of covalent compounds and how all of these things affect those actual properties. But we're just learning the mechanics right now. So what is unique about number 5? Okay, Lucas?
It's the aluminum one, and it only needs 6 to be done.
It only needs 6. So when we're looking, it's got 7 times 3 is 21 plus 3. We have 24 electrons. Aluminum, and then fluorine, and you're going to go and put all of your electrons, your lone pair around, and it's going to look like that. Your natural instinct is to follow the rules, and you're going to want to put a double bond with the fluorine to get aluminum to have 8. What are the 2 problems with that? Lucas, you just said 1. Aluminum only needs 6. What's the second problem with trying to form a double bond with fluorine?
It can't do it because fluorine doesn't want more than one bond.
That's exactly right. Did y'all in the back here what she said? Say it one more time loud.
It doesn't want to do it because fluorine can't form more than one bond.
Okay? And why can't fluorine form more than one bond?
Because it already has 7 valence left.
It's got 7. It only needs 8. It only needs 1 more. So it's only going to form halogens. Only form single bonds. Okay? There's nothing. That's it. I'm saving this for 7th grade. Halogens only form single bonds. So we're not going to form a double bond with fluorine, and aluminum only needs 1. Now, when we go to number 6, I saw some kind of crazy Lewis dot structures on Friday that we didn't have a chance to really go over. On number 6, what's the rule if you have hydrogen, oxygen, and some other nonmetal? Is the hydrogen going to go onto the nonmetal? It's going to go onto the oxygen. So we have 1 plus 7 makes 8. 6 times 3 is 18, so we have 26 electrons. Chlorine is the central atom with 3 oxygens around it. You see, the hydrogen would fit here. Everything would be octet rule. Everything would be satisfied. It would appear like, hey, this is perfect. But it's just experimental evidence, and life experience just tells us that the hydrogen is on the oxygen. Now, all 3 oxygens are identical, so pick one, any one, it doesn't matter. But the hydrogen is going to be on the oxygen, not on the central atom. Okay? So then we have 26, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Now, let's talk about the shape then. Here we have two different essential atoms. Chlorine is essential atom, oxygen is essential atom. What's the definition of essential atom? One that is in the middle between at least two atoms, right? And so these oxygens only are attached to one thing. They're not in the middle of anything, but this is in the middle and this one's in the middle. We don't say an overall shape. We simply say the shape around each central atom. So what would be the AX formula around the chlorine?
Trigonal.
Say that again?
Yeah.
It's not just AX3, not E2, just E. E is the lone pair on the central atom, okay? So we're gonna say, now again, this is not an answer, but we're gonna say AX3E. Then you go to your cheat sheet to get the answer. Anything that is AX3E is going to look like
Trigonal pyramid.
trigonal pyramidal, which looks like, where's my ammonia molecule? Can I decompose it? Right here in front of me. Okay, it's gonna look like this. So this is my lone pair. It's still 4 pair of electrons. It's still, the electron pairs are still at the points of a tetrahedron, but we lost the leg of the tetrahedron, so it's trigonal pyramidal around that one. But what's the AX? So this is trigonal pyramidal. What's it going to be around the oxygen? Does everybody, and that's just, remember, that's just a nothing, okay? Does everybody understand the AX formula? So what's the shape of AX2E2? Bent. So it's going to be bent around the oxygen here. You're going to have a pyramid, and then it's going to be bent around that, okay?
So there are two shapes.
So there are two shapes. You say the shape around each central atom. You don't say the shape around the whole thing. Okay.
That's why A always equals 1.
Yes. Okay? Did I decompose cocoa? Yeah, I did. I think I decomposed cocoa. Okay. So now I want to just look at some of these. SF4. Okay, I'm going to draw it up here just so I don't move anything. SF4, I think we already drew this. Okay, it's got 7 times 4 is 28 plus 6 is 34 electrons. So this is 32. 8 times 4 is 32. Okay, so that's 32. So where did the 2 extra electrons go? On the central atom as individual electrons? As a pair. Now, don't put them in between the bonds. Put them in the spaces between the bonds. Here, 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 or there, anywhere. But just kind of put them as a pair right there. So what's my AX formula for the sulfur? AX4E. Okay, but again, that's not my answer. That's not a shape, that's not anything. That's just a general formula that's going to get us to. So when you look at AX4E, what's the shape? It's going to be seesaw. Now, if you want to sound a little bit more, uppity, distorted tetrahedron.
Dang, Jackson, so you.
Okay?
It's a seesaw.
Seesaw. Seesaw is so much easier. Okay, now again, remember, seesaw, look, when you have these models, and you have this, the AX5, you got 5 pair of electrons around the central atom. 1, 2, 3, 4, and the lone pair makes 5. You have 5 things around it. Where's the lone pair going to come out of this? Equatorial position or the axial position? The equatorial. Anybody know? Remember why? Anybody remember why? Why out of the equatorial, not the axial? Loosen up the little circle on the side. Anybody? Nobody remembers why it comes out of the equatorial?
No.
What's my bond angles here?
Oh,
60. I mean, 120.
120 on here, what are they here?
Oh, right,
90, since it's got more space, remember lone pair occupy that greater space, so they're gonna wanna come out of the 120 bond angle, not the 90. Okay, so they'll come out of here, and so this is gonna be your AX4E, this is gonna be your seesaw shape. Okay?
They have, like you put the extra 2 on sulfur because fluorine doesn't form double bonds.
Well, you always put the extra electrons on the central atom, always. Okay, once the exterior ones have their filled octet, okay, they're not gonna have more. The central atom is the only one that's gonna have an expanded octet.
It's not like a double bond.
No, it's not. No, it's just it's the extra lone pair. The only time you're gonna form a double or triple bond is when the central atom has too few. And you gotta share to get the central atom to get more. So it's kinda like this one here, carbon, nitrogen, hydrogen, and it looks like this, okay? But carbon now, all your electrons are used, but carbon only has 4 electrons. So now I have to share to get carbon to have it, and so that's when we go and we share here and we share there. Now that gets carbon. So the only time you form double bonds is when the central atom doesn't have enough. If you have too many, there's just lone pair on the central atom, we get an expanded octet, but no double bonds. Okay? So now if I look here at BRF5, again I'm gonna have 7 times 6 is 42 electrons. And I'm just again gonna do it up here. F, 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 okay? Now that's gonna be, again, when I put all my lone pair in, it's gonna end up being 40, but I have 42. Okay, 8 times 5 is 40, so where do my extra 2 electrons go? Central atoms are somewhere as a pair. Okay, so now how many total electrons are around the central atom? How many pair? 6. But one of them's a lone pair. So I have 6, which is the octahedron, but they're all 90 degrees, so pick one, anyone. So now my shape is square pyramidal. Okay? Alright, so I'm going to let you kind of finish that kind of on your own, and I'll check it. I'll have you maybe turn it in on Wednesday when we take the test. But I want all of the Lewis dot structures, and I want all the shapes. And if there's more than one central atom, which, like on 11, there's going to be more than one central atom. On 12, there's going to be more than one central atom. Say the shape around each one. Okay? But we don't have time to kind of go through all of that now. Okay? And I know that you're going to be tempted to want to get that done, but you need to listen. Because now, we're going to continue on, and this is starting in on the most important thing. In your notes, polar bonds and polar molecules. Why do we have, where does Santa Claus live? At the North Pole. Where do the penguins live? South Pole. What does it mean that the Earth has a North Pole and a South Pole? Right. It's like the Earth's like a big magnet, right? We have a North Pole and a South Pole. It's the magnetic fields. Okay, so we got a positive end, a negative end on the Earth. So the Earth has poles. So when we talk about molecules being polar, it's just like the Earth. The Earth's got a North Pole and a South Pole. Molecules can have a north and south, or a positive and a negative end. They can be polar. Well, what causes molecules to be polar? Well, polar bonds, in a covalent bond, what's supposed to be happening with the electrons?
Shared.
They're shared. But if you know anything about anything in relationships, when you go to share something, sometimes it's not an equal sharing. Okay? If you're the older brother or sister, you feel entitled that you ought to be able to have it just more than the younger brother or sister. If you're the younger one, you just have to learn to deal with it, unless you're a mama's boy. And then you say, Mom, and and then she always favors the youngest, because I was the last of 5, so I was, the self-proclaimed favorite. So, I would always be able to just whine, and then just my brothers would have to share with me. But a lot of times there's not always an even sharing. So polar bonds result from an uneven sharing of electrons, which cause the shared pair of electrons to hang out around the more, here's this word, electronegative. Whew, electronegative. What is electronegativity? That was last unit. We did it quickly. Electronegativity. Anybody?
I forgot.
See, we're trying to avoid this memorize, regurgitate, forget part. We're supposed to learn, store, and be fascinated for life with this information.
I pressed it quickly.
You were going to say something over here? You remember what it is? Somebody was saying something over here. No? Electronegativity. And you put this on the side, the electronegativity. An atom's attraction for a shared pair of electrons.
What unit was this in?
Do what?
What unit was this in?
You gotta talk loud enough for me to hear you.
What unit was it in?
That was just periodic table. That was one of our trends. Okay, so what that means is here's water. What this pair of electrons is being pulled towards the hydrogen, it's being pulled to the oxygen. It's a shared pair of electrons. The electronegativity is a scale, it's a tug of war. You have a positive nucleus on hydrogen, you have a positive nucleus on oxygen. Each one of those nuclei are pulling and attracting those electrons. It's a Coulombic attraction, a positive to negative attraction. But the electronegativity is a scale of measuring how much does each atom attract that shared pair of electrons. Remember, it's the scale from 0 to 4. This is the weak, this is the strong attraction. There's not a whole lot of differentiation, just 0 to 4. Now, does anybody remember where the most electronegative elements are found?
0.
Which are the most electronegative elements on the periodic table? Where are they? They're on the right side and the top. Fluorine is your most electronegative element. Most books put it at 4, top of the scale. Your periodic table gives you at 3.98. Okay? So where would the lowest, least electronegative element be? Bottom left, francium. Okay? We need to know that trend. But your big 4, the elements that share, that hog the electrons, they're bad sharers. Okay? We're going to use the acronym phone call. F-O-N-C-L. Okay? The most electronegative elements are going to be phone call. F-O-N-C-L. Can you see how I can get like a license plate, get phone call out of that? If one of those elements are present, they don't share electrons. They hog them. They're the only ones whose electronegativity is greater than 3. Fluorine's is 3.98. Oxygen's is 3.44. A lot of books put it at 3.5. Chlorine on this periodic table is 3.16 and nitrogen is 3.04. Many books put nitrogen and chlorine both at 3.0. Regardless, they're the only ones that are above 3. They're the most electronegative elements. So when they go to share, like even here, It's not an even sharing, it's an uneven sharing. So if I had put two hydrogens together, what do you think that means as far as the attraction for this shared pair?
It's equal.
It's going to be equal, right? Which means that the electron cloud is going to end up being perfectly symmetrical, and there's not going to be any poles. The electrons aren't going to hang out one side more than the other. But if I put hydrogen with chlorine, chlorine is 3.16, hydrogen is 2. Your periodic table changed it. I think it says 2.18 now. Okay? Well, on a scale from 0 to 4, that's pretty much, that's like a whole 25% greater. Now, it's not strong enough to completely pull the electrons away, because that's going to happen when you have a low with a high. That's a metal with a nonmetal. Now the nonmetal just doesn't share the electron, it just transfers the electron. But two nonmetals, when the electronegativities are the same, it's kind of like when you're in a tug of war, you got the flag, you win. Well, what's that Korean one when you have the tug of war, but you go over the cliff or something when you...
Squid Game.
Squid Games, yeah. I've never watched it, I've just heard about it. Okay, you're doing Squid Games, you're fighting, but you're fighting for your life, and so the flag is moving more one side than the other, but it doesn't get to where you fall off the cliff. It doesn't get to where you win. It's just an uneven sharing. Now, the more uneven the sharing is, then the more the flag is over on one side, the more the electrons. So here now, the electron cloud is going to be way distorted. So the electrons are going to be much more near the chlorine than the hydrogen, because chlorine's electronegativity is greater. What's the charge on an electron? Negative. So that makes this side, remember it's polar, it's not a transfer, so we're not getting ions, so we're not getting a positive and negative, we're just getting poles, we're just getting a positive and negative end. And so which chlorine is going to be which one? Okay, if the electrons are being drawn to it, what charge are on the electrons? Negative, so therefore the chlorine is going to be negative. But to differentiate it from an ion, to say that it's not really a complete transfer, it's just an uneven sharing, we're just getting a partial negative, we're going to use that delta symbol. Okay? That means partial, and we're going to have delta positive. That means this is delta. That means partial negative. And this is partial positive. Now we have this scale, 0 to 0.4. We're going to say if the differences in electronegativity are less than 0.4, the difference, X is the difference in electronegativity between the two atoms. If it's less than 0.4, they're pretty close. The flag's still going to be pretty much in the middle. Okay? That's going to be like the freshmen versus the sophomores in a tug of war. It's going to be pretty even. It's not going to be too bad. Okay? So we're going to call this nonpolar. Covalent. Okay? It's a nonpolar. No poles. Even sharing. So if you want to say nonpolar means an even sharing. But if the difference is between 0.4 and 1.7, now this is an uneven sharing, so we're going to call it a polar covalent bond. Which is an uneven sharing. But if there's a huge difference, X is greater than 1.7, big difference. Now this is the difference between the two elements. What type of bond is that going to be? Ion. That's going to be a transfer of electrons. Now, All of those electronegativities are on the backside of your periodic table. Okay? If you want to be technical, every time we have a bond, you go through and you have to look them up and you subtract them and you find out where it fits on the table. We're not doing any of that. Okay? We're just going to use trends. We're going to use phone call. If fluorine, oxygen, nitrogen, or chlorine are involved in the bond, more than likely it's going to be somewhere in this range. It's going to be a polar bond. If it's two nonmetals but phone call is not part of it, more likely there's not much difference going to be in the electronegativity. It's probably going to be a nonpolar bond. So we're simply going to look for phone call to determine whether or not we have a polar bond or not. Okay? So here are some of your examples. I mean, if you want to fill in examples, I did the examples first. Okay? You got hydrogen bonded to hydrogen. Okay? The difference in electronegativity is 2.18 minus 2.18 is equal to 0. It's nonpolar. You have hydrogen bonded to chlorine. You have 3.16 minus 2.18, which is going to equal 0.98, 2.18, 3.16, yeah, 0.98. That's going to fit right into here. That's going to be a polar covalent bond. This is non-polar covalent. And uneven sharing. And if you want, you can, I don't know where you drew these, but they can kind of be drawn by it. So we're just going to look for anything with phone call in. Okay? Now again, technically you go through and you can subtract all those and the value's always going to be given, but we're just going to look at our trends. So we know lowest with the highest, biggest difference, ionic bond. Two nonmetals, the electronegativity is going to be much closer to one another, and as a result, generally speaking, it's going to be a sharing, but if phone call is involved, it's going to be an uneven sharing, whereas if it's, a sulfur and iodine bonding or whatever, they're going to be pretty close to one another. There's not going to be a big difference in electronegativities. Okay? So we're just going to use the general trend. We're not going to get specific on that. Okay? Phone call. All right. I need to just get through this last concept, and then tomorrow we'll practice and look again, looking at the sheet that we have all those Lewis dot structures, go through, and then just kind of determine the molecules polar or non-polar. So this is just polar bonds. How do we tell if the bond itself is polar? But what about molecules where there's more than one bond? This is where the shape comes into play. Does everybody have all this? Beautiful, beautiful. Look at all this high-tech terminology. Electronegativity, polar bonds, non-polar bonds, covalent, ionic. You guys are learning some stuff. All right. This is where we're going to end for the semester. Right here. Okay? Well, technically for the year. Polar molecules. They're the ones that have a positive and negative end of poles. And just like the HCl, it's a polar molecule. Now, it only had one bond. Okay? There are two criteria for a molecule to be polar. Number one, they have to have polar bonds. And this is, again, where we're just going to look for phone call. That's our acronym. If there's phone call in the molecule, it's probably going to be polar, unless they're bonded to themselves. Obviously, if fluorine is bonded to fluorine, what's the difference in electronegativity going to be? Zero. Okay, so we have to use some common sense there. But if it's bonded to anything else, now here's the deal: polar molecules must contain at least one polar bond, and not or. And polar molecules must be asymmetrically shaped. And y'all, when you spell the word asymmetrical, there's only one S. You do not want to be an ass. Okay? Okay? There's only one S in asymmetrical. I'm just trying to help you on your spelling bee.
Oh, that's
Okay.
okay. That's what you understood.
Okay?
It's okay. It's
Oh, Mr. Hobbs said ass on video. Oh no. Send this to the administration. Okay. Tetrahedral. So let's look. Tetrahedral molecules are symmetrical if all four atoms are the same. Okay? Because what happens with CCl4 CCl4, okay? There's phone call present, right? So the electrons are being drawn towards the chlorine this way, but they're being drawn this way, they're being drawn that way, and they're being drawn this way. Now the reality is that it's three-dimensional, so it's going to look like this. So they're being drawn this way, this way, this way, and this way, but it's symmetrical. So if you take physics, you'll find that if you deal with vectors, if you pull equally in all directions, it's not going anywhere. The pulls all cancel each other out. So we can have four polar covalent bonds, but because the molecule is symmetrical, it's nonpolar. Okay? So that's why it has to be an and. Symmetrical molecules are automatically nonpolar. Doesn't matter what type of bonds there are. Symmetrical molecules are automatically nonpolar. But if it's asymmetrical, if I just go ahead and put a hydrogen onto here, or let's just say I put one chlorine on here. Okay? Well, let's just for the sake of this, let's just, even though it's opposite, these are my three chlorines and this is my hydrogen. Well, now I have a pull this way, pull this way, pull this way, but the hydrogen's electronegativity is not anywhere near what chlorine's is. So all of a sudden we got a weak side over here, so now there's a net pull down. So now we have a negative end, or an uneven distribution of electrons, so we get a negative end and a positive end. Because the atoms aren't all the same. All my bonding atoms aren't the same. The only time it's going to be symmetrical when all your X's in AX4, all the X's have to be the same. Now, don't be confused. If I did a molecule like this, my Lewis dot structure looked like this. I should have just moved it over just a hair. Okay? My Lewis dot structure, and again, forget that. Okay? My Lewis dot structure looks like this. That looks pretty symmetrical, doesn't it? Do not trust your Lewis dot structure shape. Okay? Because you're looking at something in 2 dimensions that's existing in 3 dimensions. So if I do this, okay, this is what it actually looks like. So it's pulling this way and the chlorine's pulling that way. There's nothing balancing it out. You're looking at it kind of like this with no depth perception, or you can even say like this, no depth perception, where the chlorines are on each side, but the reality is it's not flat. If it were flat, then yes, it would be symmetrical and nonpolar, but it's not flat. It's a tetrahedron, and so no matter where you put these chlorines, they're never going to cancel, the poles aren't going to cancel each other out. So just trust this. It's asymmetrical if the X's are not all the same. Okay? In trigonoplanar molecules, trigonoplanar, SO3, SO3 looks like this. Okay? So the oxygen's pulling here, so can you see that if you pull equally here, here, and here, all 3 pulls are going to cancel out? It's a symmetrical molecule. But if I have, again, if I change this to where now I have something along these lines, now they're not even pulls. Chlorine's got different electronegativity than oxygen, and so they don't all balance themselves out. It's asymmetrical. It's only symmetrical if all three things are the same. And then linear molecules, they're symmetrical if both the same. So CO2, and then I keep dropping that. The CO2, I know I have a CO2 built here. Do I not have a CO2 built? You guys built it. On your sheet, what's the shape of CO2?
Linear.
It's linear.
How old
Okay.
was Connor?
So here's CO2. Okay, so even though the pool's going to go this way and that way, they're going to cancel each other out, not go anywhere. It's symmetrical, so they balance each other out. But in your HCN looks like this with a lone pair. Okay, let's just make this is a nitrogen and this is a carbon. It's going to look like this. To visualize. Okay, so here's your HCN. Here's your carbon, your nitrogen, so again, here's my central atom. The nitrogen's got a much stronger electronegativity than hydrogen does. So the electrons are all going to be drawn this way. So we're going to have a negative pole over here and a positive pole here. It's asymmetrical. Okay? So as a result, it would be a polar molecule. You've got phone call present, and it's asymmetrical, so it's going to be polar. Now, one other little clue, which it's tricky for me to give you this tip. Most, but not all. And do you have this? Let's look at this sheet right here. Okay, so all of our shapes, if there's a lone pair on the shape, more than likely it's asymmetrical. But we can't say always because there's two exceptions, and so you probably want to write these exceptions down on this sheet. When we're looking at this, now look, yes, now hold on, I'm going to really reinforce this. It is not the lone pair that makes it asymmetrical, okay? It's just that most asymmetrical shapes contain a lone pair. Okay, so you don't say it's asymmetrical because it has a lone pair. It's asymmetrical because it's shaped. But most shapes that are asymmetrical contain a lone pair. But you can't say always because there's two exceptions, which I'm about to show you. So if I looked at AX6, if all X is the same, then it's going to be symmetrical. But even if they're all the same here, the shapes, this one is going to be asymmetrical. But this one here is an exception. This is why we can't say it always. Because it's the square planar one. So even though it's going to have two lone pair, it's still going to be a symmetrical molecule. It's one of the two exceptions to where we have lone pair, but it's still symmetrical. As long as the X's are the same. Okay? So, square planar is going to be symmetrical. Trigonal, this as long as the x's are all the same, this is gonna be symmetrical. But this is gonna be asymmetrical, asymmetrical, asymmetrical. Actually, this is the other exception. This is your other exception. Because it's linear. So you're gonna have one on both sides. So it's gonna end up being symmetrical. So there's two cases where you can have lone pair, okay, but it's still gonna be symmetrical. Everything else, if there's lone pair, all the rest of them, if there's lone pair, it's asymmetrical. Okay? So in our last 5 minutes, let's just kind of look at some examples. Whoop. I'm knocking everything off. Okay, you already have all these drawn. CBr4. CBr4. Okay? First off, do I have any polar bonds? No. Okay? Now we could go and look, and if you wanted to look, you would see that bromine's electronegativity, I believe, is 2.76. Bromine's electronegativity, how do I get on the word? Yeah, top right corner, bromine. 2.96 for bromine. Okay? Whereas hydrogen's is 2.18. So actually we might end up slightly into the polar range, where we go 2.96 minus 2.18. However, is it symmetrical or asymmetrical? Symmetrical. It's AX4, all the same, symmetrical. Therefore, what's this, polar or nonpolar? Nonpolar. Now what does it, let's just make sure we know. What does that mean, it's nonpolar? It's an even sharing. There's no positive or negative end. The molecule is neutral all the way around. It's a perfectly, the electron cloud is perfectly evenly distributed. There's not a positive or negative end. That's what non-polar, no poles, means. But on PCl3, it looks like this. So my shape, you already did the shape, it's trigonal pyramidal. Okay? Do we have phone calls? Do we have a polar bond? Yeah. It's 3.16 minus 2.19. Those are the electronegativities. However, is it going to be symmetrical or asymmetrically shaped? Asymmetrically shaped because one of them is going to be a lone pair, so it's pyramidal, so we got to pull this way, this way, this way, but there's nothing pulling up. So as a result, we end up with a polar molecule. You have 3 polar bonds and you have a polar molecule. Okay? So here we go CO2. We already talked about this one. CO2 looks like this, linear. So what do we, is it symmetrical or asymmetrical? So what does that mean in terms of polarity? No poles, non-polar. Now just to compare, when we look at water, even if I draw water like this, what's the shape of water? AX2E2, bent. Is that symmetrical or asymmetrical? Do I have phone call present?
Yes.
Yeah. So is this polar or non-polar? It's asymmetrical. It's got polar bonds. So it's polar. It's very polar. Okay? And again, this right here is why CO2 is a gas. This right here is why H2O is a liquid. Linear, symmetrical, bent, asymmetrical, non-polar versus polar. It's going to determine the properties of the substance, which makes water a liquid at room temperature and CO2 a gas. And we thank God that, if it weren't the case, life as we know it on Earth would not exist. The fact that it's bent, asymmetrical, and polar. Tomorrow we'll just go through and practice looking at all these, being able to identify if they're polar or non-polar, and then we'll start getting ready for the test. You have your study guide that is, optional, but it's due 7 o'clock tomorrow night. You don't have to wait until 5 till 7 to try and upload it, because it's going to take a minute. Okay? Plan ahead. Okay? I have it set to not accept after the time. All right? All right, y'all have a good rest of the day and go Jags.